So here's a cartoon of basically the problem. So we burn 8 billion tons of carbon a year and put it in the atmosphere. You multiply that by 4.4, so it's about 35 billion tons of carbon dioxide. The ocean absorbs a couple of billion tons of that carbon from the atmosphere every year, which is good, otherwise the situation would be worse. The bad thing about that is it increases ocean acidity. And then about 50% of the difference is retained in the atmosphere. So that's every year we add a couple of gigatons to the atmosphere, and that's actually what drives the carbon dioxide levels up. The other scary thing on this graph is that there's still 1,600 billion tons of carbon in fossil fuels in the ground. So if you put half of those up there, it's sort of game over. So it's not a matter of running out of fossil fuels or peak oil. It's a different problem. So what's the result of that carbon dioxide rise? This is it. For every large red dot there, that's about a 6-degree Fahrenheit increase in temperature in the last 25 years. So this overwhelmingly demonstrates to you, I think, this is from the Stern report, the British assessment of climate change. I think it shows you the overall warming trend very visually. Pretty hard to deny that evidence. So here, in fact, I think the question for our times, what temperature as a society we want to choose? And this is why I'm sort of calling climate change an aesthetic problem. We're choosing the aesthetic of the future we want to live in. We're choosing the environment we want to live in. Right now, we're choosing by not choosing. We should choose by actually choosing, if you know what I mean. We're sort of allowing ourselves to go somewhere rather than having an end goal we want to go to. So how might you go about, and I'm sorry, I'm going to have to describe this graph because it doesn't look like the contrast is very good. How would you go about choosing where humanity should go? So there's three types of things that you often hear about in the media associated with climate change. One is a climate model. So that a climate model is basically a really complex physics and chemistry simulation of the atmosphere and everything, and that basically shows us how heat will flow around the planet, etc. We run scenarios in those models, and a scenario is something like, if humanity continues business as usual, sort of doing what we do, how much carbon dioxide does that add to the system? And you run that scenario through the model, and it sort of predicts the temperature outcome. The thing that makes all the headlines are things called impact studies, and these impact studies take the results of those two things and say, at 1.5 degrees Celsius, we predict that you'll lose 10% of species. At 2.5 degrees, you'll lose 15 to 40% of species. At around 2 degrees, you'll lose 90 or 95% of all coral reefs. 3 degrees, there'll be 1 to 4 billion people, more than the existing 1 billion people facing water shortages. And this is sort of the litany of horrors, right? And that's all the headlines. So imagine you were trying to figure out what temperature am I going to choose for the planet. Pick the level of horrors that you're going to be happy to tolerate. And the consensus is 2 degrees is probably the most horrible you want to go. One of the reasons for that, it's not showing well here, is there's a whole bunch of nonlinear feedbacks. Like you melt the tundra in the north, and that releases a whole bunch of methane. They predict that will happen at 2 degrees. The sad news is, and I spent Wednesday at Harvard with climate scientists, is it looks like that methane is melting earlier. So what we're probably going to find out is we should push this line down in the next 5 years as we learn more. So anyway, you pick your horror level, and let's just say that's 2 degrees, and we're going to accept losing 10 to 15% of species and nearly all coral reefs. And then you say, what concentration of carbon dioxide in the atmosphere will hit me that temperature? And this is sort of the error range. So if we stabilize the climate at 450, the best case scenarios will get 1.5 degrees, the worst case is 3.5. Roughly, you've got a 35% chance of hitting 2 degrees if you stabilize at 450. So let's say we accept the horrors, we accept that we only have a 1/3 chance, so let's shoot for 450. People much smarter than I, James Hansen, who's sort of America's principal climate scientist, he actually argues very reasonably that we should do 350. Unfortunately, I wasn't even born when 350 passed. So that's pretty challenging. So that's to put that in perspective. I'm going to have to make a joke soon because everyone's looking depressed. I will have some funny slides, I promise you. So this is what we've chosen as the aesthetic of the world we want to live in, 2 degrees, 450. How do you hit that? You have to roughly do something like this, reduce the 8 gigatons to 1 to 2 gigatons going into the atmosphere. That'll balance roughly with this. The other disappointing thing is scientists are finding the capacity for the ocean to absorb it is decreasing, so maybe that's not true, so maybe this one has to be even lower. Another way to look at this is, this was actually known in the early 1990s. This is like the simplest climate model you can have, or a carbon dioxide model. Basically, for every billion tons of carbon you burn, you add 1/4 of a ppm of CO2 concentration in the atmosphere. Or for a terawatt year of energy, you add this much ppm to the atmosphere. And so as we know how many ppm we've got to go to 450, which is about 60, we actually know how much fossil fuel we can burn starting today. We've got about 400 terawatt years of fossil fuel left to go. So that means we've got 40 years at 10 terawatts, or 20 years at 20 terawatts. 20 terawatts is roughly what they think we'll be burning in 2020. 10 terawatts is a little less than what we are burning today. So I think that puts a very concrete sort of perspective on using fossil fuel energy. I might skip this one.